You may recall that an acid and a base react to give you salt water. Yes, in a double displacement reaction. For this particular chapter, what we're interested in is this salt. If you put salt into water, that is, let's say you have a glass of water and you just put some salt in it, what does that do to the pH? Well, there's 4 different scenarios that we can look at. 4 sources of salts from acids and bases. You can have a strong base and a strong acid reacted together to form a salt. You can have a weak acid and a strong base. You can have a strong acid and a weak base. And you can have a weak acid and a weak base. So, depending on what you have, I will give you the punchline of it. A strong acid and a strong base are always going to give you a pH of 7. A weak base and a strong acid, it's going to be acidic. My memory thing is the base part's weak and the acid part is strong, so it's going to be acidic because this is stronger than that. Right, okay? So a strong base and a weak acid. The base is the stronger part, so it's going to be basic. And then a weak acid and a weak base. Well, what's it going to be? Well, it depends on which one of these are stronger, if you will. Well, how are we going to know that? We're going to look at, as you know, Kas and Kbs. That will tell us relative strengths. Now, where it gets further confusing is for a weak acid and weak base, that gives us 3 scenarios. If Ka and Kb happen to be exactly equal, well, it's going to be a pH of 7. That's a rare occurrence, but it does happen. If Ka is greater than Kb, well, that's going to mean your acid is stronger than your base, and so just like before, that's going to be acidic. Likewise, if your weak acid is even weaker than the weak base, then the weak base is therefore stronger than the weak acid, and that winds up being basic. And so there's your scenarios that you can have. This is taught a bunch of different ways, but the way that I understand it best is I take a look at the salt and what I'm going to call deconstruct the salt. So I want you to take water, break it apart into H plus and OH minus, and then try to deconstruct the salt and determine what base it came from. So here a base is plus. This obviously came from BOH. And so if this B combines with this OH to give you BOH, what's left? The H plus is left. So we, in essence, have a balanced chemical equation there. Likewise, what's the anion going to connect to? The H plus. There's your HA, and what's left over? The HO minus. And so I look at these 2 equations. I look at the equation from the strong acid, or from the acid that would have given me the acid anion, its conjugate base. And I look at the base and see what would give me its conjugate acid. Okay, and I'm going to use this to basically rationalize how we work through this. Okay, so here we go. So the first scenario we want to consider is, now you already know the answer to this because I've told you the strong acid and strong base, right? But let's go ahead and look to see if we can rationalize that. Okay, so what would sodium come from? Well, the Na plus obviously came from sodium hydroxide. See, the sodium is going to combine with the OH to have come from sodium hydroxide. And then we've got this H plus. Okay, here's the deal. So if we have an equilibrium here, you're going to get some H plus generated. Well, guess what? But we know if since this is a strong base, it disassociates 100%, which means there is no reaction going back the other way. If there is no reaction going the other way, there's no H plus generated. Hold that thought. So on this side, we get no H plus. So let's see what happens to the other piece of the salt. Well, Cl is going to interact with the H to give HCl, and then that's going to decompose back to Cl. So now we have an equilibrium set up here. But we really don't. Why? Because this is a strong acid, and by definition, strong acids dissociate 100%, which means this is a one-way arrow. If this is 100%, this is 0%. So this doesn't happen. So there's no hydroxides generated. So what this means is, if you've got none of these and none of these, you're not generating an excess of H+, from this, and you're not generating excess of HO minuses from this. They exactly cancel each other out. None of these is formed. So the pH remains 7. Okay, to better understand that, I think, a weak acid strong base illustration. Let's look again at sodium. Okay, let's deconstruct our acid. So what did the sodium come from? Sodium hydroxide. But we've just said the sodium doesn't go back to sodium hydroxide. That doesn't happen. So this is a one-way street here. In other words, this doesn't happen. The sodium ion stays sodium because it can't go back this way. If this reaction is stopped, then that's stopped. But look at what happens with acetate. Can acetate actually decompose to form acetic acid? Absolutely. Why? Because this is a weak acid. And we know it has an equilibrium constant. So we know this happens and this happens. So if you have 100% of this material, you know because there's an equilibrium constant, some HAC has to form. Some acetic acid has to form. But guess what? If it gets the H from water, guess what else it generates? An HO. So what do we have? No H plus is generated here. A hydroxide is generated from this species. And so guess what? There's a net gain in OHs, and so it winds up being basic. Let's look at the next scenario. A strong acid and a weak base. So let's take our salt. And first of all, let's just take this part, nitrate. So what does that do? Well, we know it doesn't go that way because it disassociates 100%. It only goes this way. So once we have this material, since none of this forms, none of this can form. So we're not going to get any excess hydroxide. But let's see what happens with the ammonium part. Well, we know ammonium is the conjugate acid of ammonia. Now, rather than I'm going to put like we did before, we're going to put our chemical species in here, and I'm going to have the ammonium bond with this, and so there's your OH, and it gives you an H+. So look at what happens. No OH is generated by the anion reaction, but there is some H+ generated from the cation portion. Therefore, you get an excess of this. Therefore, it winds up being acidic. And now you're getting it, hopefully. So here we go. Let's look at the fourth scenario. A weak acid and a weak base. Okay, so here we go. This time I'm going to show this a little differently. Instead of break it down this way, I'm just going to kind of cheat. Instead of do that hydronium ion thing, I'm going to leave it like this. So what happens? Ammonium breaks down into NH3 plus H+. That's the equilibrium reaction. Acetate breaks down into acetic acid, and we know that's going to generate a hydroxide group. So what's the net deal? We can see that the cation is generating some H+, and the anion is generating some hydroxide group. So is it going to be acid or basic? Very simple. If Ka is greater than Kb, that means Ka. And this is, by the way, Ka for your conjugate acid. If Ka for your conjugate acid is greater than Kb for your conjugate base, and look at this. That means this is going to go to a greater extent than this. And that means if this goes to a greater extent, you have more of this protons generated than these hydroxide, so it's going to be acidic. Likewise, if Kb is larger than Ka, then you're going to have a net basic because more hydroxide is going to form than protons. And finally, if these dissociate to exactly the same extent, then they're going to cancel each other out and just make water, and the pH is going to remain 7. So basically, when you get a strong acid, strong base, or whatever type of problem, you already know about what the answer is going to be. You know whether it's going to be net acidic or net basic or charge neutral. And that's the point at which when we do that head-east thing, if you work one of those problems, you can test your answer and make sure if you have a strong acid, weak base problem and you don't get a pH less than 7, you probably missed it. because you know the general range that that's supposed to be. Okay, so those are kind of general rule of thumbs. So let's see what a problem might look like. Ammonium fluoride is added to water. Okay, so what do I recognize this as? Immediately, if I'm working this problem, you have to see that as a salt. So already you know you don't have a strong acid or strong base or weak acid, weak base problem. You have a salt problem. Yes? Okay. Is added to water. Okay, so we know we're going to set up an equilibrium with water. If one of these does it dissociate into a strong acid or strong base? Is the resulting solution acidic, basic, or neutral? Or not enough information to determine? Okay, well, let's see. And it gives Kb and it gives Ka. So let's take a look at that. So let's just dissociate this. We know we have this reaction going, and we know for this reaction, Kb, ammonia is a base. Kb for ammonia is 1.8 times 10 to the minus fifth. Okay, and it tells you right there, ammonia, not ammonium, this is ammonia. So we're putting the Kb for this reaction here, for that reaction there, where ammonia grabs a proton and goes to ammonium. Yes. Okay, so let's see what else we have. Fluoride, what does it do? Is it going to set up an equilibrium with hydrogen fluoride? Absolutely. Why? Because this is not a strong acid, it's a weak acid. If it's a weak acid, it must have an equilibrium constant. So we know some of this is going to break down. If it forms HF, then what's going to be generated? Hydroxide, so I can see I'm going to generate some of those. Now I know I'm already generating some of these as controlled by this amount. And I'm going to get a certain amount of these controlled by this amount. Now notice it says Ka. Ka for what? HF. Now notice, this data is given for the materials. That's why if you don't use this approach where you deconstruct it, it gets really, really confusing. So deconstruct it, and normally you will see what it is, the data that's either given or that's in a table. Okay, so now which one of these are we going to work this from? Okay, so let's look at Ka. So what is Ka for ammonium? Because we're interested in the Ka for this, yes? Because that's where we're starting. So we know that Ka times Kb is equal to Kw. So we know that there's the Kw, and there's the Kb part we solve for Ka, and Ka for this species is 5.5 times 10. So that's the Ka I'm interested in. That's the Ka I'm going to compare to this Kb. I'm going to compare that Ka to this Kb. Okay, that Ka to that Kb. Okay, here we go. So what do we know? Well, it gives Kb for this, but I'm not interested in Ka for that. I'm not interested in Ka for that. I'm interested in Kb for this, for my anion. So what do we have? Ka times Kb is equal to Kw. Therefore, Kb is equal to Kw divided by Ka. There's my Ka, and I do that, and I get 0.14. So now I have to compare these two. So which is larger? Well, it looks to me like that the Ka is much larger than the Kb. Let's do one more problem. Calculate the pH for a 1 molar solution of this. The key is to recognize that as a salt solution. Once I recognize that as a salt, I'm going to deconstruct it. I see this must come from a strong acid, so I don't have to worry about this because that reaction is not going to occur that way. And this is derived from a weak acid, so I know now I do have a Ka associated with that. Right. And so that means I also have a Kb associated with the conjugate base. So let's see what happens. I need to know about now I'm interested in pH, so I want to know what the concentration is here, right? So what am I going to do? I'm just going to use my weak base formula here and try that. So I'm merely just going to solve this. At this point, what do we have? We just have a weak base problem. So we just plug and chug into that, and we wind up with pH is equal to 11.2.